All right, let's just give it another minute so folks can join. Okay, it seems like we're approaching a steady state. Welcome everyone to the RC Fluxes from Space webinar series. Today, it is my pleasure to welcome our own Sarah Gille, who will give us some updates about ODYSEA and other interesting RC things. Take it away, Sarah.
Thank you, Bia. Yeah, I'm going to talk today about ODYSEA, which is a satellite proposal to measure it's called ocean dynamics and surface exchange with the atmosphere. And the goal is to measure winds and surface currents simultaneously using a satellite Doppler scatterometer. This is a joint project with JPL and CNES, the US and French participation. So it has a large US and French science team. And ODYSEA is really targeting the same things that the Air-Sea Fluxes from Space webinar series is targeting. It's thinking about the fact that ocean interactions with the atmosphere, my slides to advance, are really critical. The ocean drives our disruptive weather. It's the source of water that brings rainfall to California and the US West Coast in the winter. It's driving catastrophic torrential rain that occurs at other times of year. And when we think about hurricanes, and a number have struck the US this year, including one that's taking shape just this week in the Gulf of Mexico. Those are really storm systems that depend on understanding how the ocean and atmosphere talk to each other. So ODYSEA is slotting into this knowledge gap by trying to ask about momentum exchange between the ocean and atmosphere. This is just a quick summary of what the mission is doing. It's a Ka band Doppler scatterometer that's intended to provide the first ever global measurements of total surface currents and the winds overlying those currents. And with measurements close to the coast, 5-kilometer postings and a swath width somewhere between 1,500 and 1,700 kilometers. It's being proposed to NASA's Earth System Explorer program, and it's currently one of 4 missions that are under consideration. So there's detail here about the deputy PIs, Melanie Fewings and Mark Barassa. Tony Lee is the project scientist, and the French lead is Fabrice Ardouin. But what I want to do today, though, is talk about 3 things. First, I want to give you an overview of how ODYSEA's measurements and how ODYSEA is intended to make its measurements. Then I'll talk about what we hope to do with the ODYSEA measurements if the satellite is selected. And I'll finish up by talking about the status and about ways that the broader community can get involved. And I hope that will trigger some useful discussion about opportunities for the entire community. So when we talk about measuring winds from space, we're always talking about capillary waves. Capillary waves are the 1-centimeter finger-sized waves that you see on the surface of the ocean or a lake or a puddle, if there's any wind at all. And they have the interesting feature of lining up so their crests are roughly perpendicular to the wind. So that means that if you bounce a radar signal off the capillary waves, that has useful traits. If the ocean were completely flat, if there were no wind, then a radar bouncing off the surface would be reflected away like a mirror, and nothing would come back to the satellite. But in the presence of waves, there's backscatter in all directions. And so there's a signal that comes back to the satellite. And the art of scatterometry is in measuring this backscattered radar signal. So what people have realized is that depending on the angle of the wind relative to the angle of the satellite, that's the x-axis here, you get a varying amount of backscatter. So in this example plot with a wind of 15 meters per second, you can get vastly different amount of backscattered energy coming back to the satellite depending on the relative orientation of the wind and the satellite radar beam. And what that means is that in this case, depending on the incidence angle, a 15 meter per second wind with one wind orientation might look exactly like a 10 meter per second wind with a different wind orientation relative to the satellite. So what that means is if you can measure from not just one angle, but multiple angles, you can hope to figure out both the wind speed and the direction. So the goal in a scatterometer is to obtain wind speed and direction by looking at the same patch of ocean several times. QuickScat did this using a double beam system. So an outer beam labeled V-pole and an inner beam labeled H-pole, both on a rotating antenna. So the system rotated around and got 4 looks at each patch of ocean and then used that backscattered energy to identify wind speed and direction. What ODYSEA does, which is a real innovation, is to use a Ka band signal that is very low noise. And that means that with just 2 beams, it's able to obtain, so just a single beam, 2 looks at each patch of ocean, it's able to obtain data with about the same or better quality than we were getting from QuickScat with much higher resolution. So with Ka band, ODYSEA is designed to achieve 5-kilometer resolution. And that's a real innovation that gives us the opportunity to look at things in ways we haven't looked at before with scatterometry. ODYSEA does a second thing, which is really innovative. In the past, when we've looked at radar signals from space, we've looked at the backscattered energy, but we've never looked at the phase of the radar signal. And ODYSEA takes advantage of the radar phase to learn more about the signal. So if you imagined having a stationary ocean surface and I guess a stationary satellite, the phase lines would just emanate uniformly in all directions, and we'd measure them in a straightforward way. But if the ocean surface is moving with currents, for example, then the capillary waves ride on those ocean currents, and the phase reflected back to the satellite or backscattered back to the satellite will be Doppler shifted. So there's a different phasing of the signal depending on what direction you're looking. So ODYSEA is designed to take advantage of that by taking multiple looks at the same surface of the ocean to figure out, using the Doppler shift of the radar signal to figure out the current speed and direction. So that's a real innovation that gives us an opportunity to look closely at both the winds and the currents. This is not a new concept. ODYSEA was first proposed by Ernesto Rodriguez as a concept in 2013 as a Doppler scatterometer. The Doppler scatterometer went through NASA's Instrument Incubator program. An airborne instrument was built and tested. And that airborne instrument has been the basis of SMODE, the Submesoscale Ocean Dynamics experiment, over the last 5 years. It's produced fantastic results. And ODYSEA's goal is to take that proven technology and put it onto a satellite so that we can obtain global scale measurements. ODYSEA will give us a really big improvement in the spatial and temporal coverage that we can get for winds and currents. Here we're looking at wind resolution from a variety of different satellites. So QuickScat, which is now defunct, or a couple of the European scatterometers, the ASCAT type, give fairly good global coverage, but with resolutions around 35 to 40 kilometers. COVER, which is a passive instrument on the space station, has similar coverage. There are other technologies using SAR, synthetic aperture radar systems, that can give very high resolution wind coverage, but with tiny postage stamp spatial coverage, so very little sense of a global system. And ODYSEA is in this sweet spot of providing 5-kilometer winds with near global coverage almost every day. For currents, issues are comparable. ODYSEA will give us not 5 kilometers, because we'll have to do a little averaging to beat down the noise, but sort of 25-kilometer coverage for ocean currents, and will provide total ocean currents. In contrast, from altimetry or SWOT systems, we can obtain geostrophic currents, but we don't obtain the total current. And from SAR-based systems, we can obtain currents, but not with anything resembling global coverage. So this is a real advance in our ability to sample the world. And one of the important things is that we're looking at winds and currents at the same time. Now, I should rant a little about this, because when we measure winds from satellite, we are always measuring winds relative to currents. And it's the wind relative to current that drives ocean circulation. So it's what we want. That might lead you to say that if we only wanted winds relative to current, we'd be set. But of course, we actually want to understand everything we calibrate to involves measuring winds from moorings or fixed points where we don't know the relative currents. So winds and currents interact together in interesting ways. And the example shown here really tries to illustrate this. Imagine an ocean eddy, this circular line, with a uniform wind blowing over it. On the north side of the eddy, the wind is blowing counter to the ocean current, and that makes the effective wind much stronger. So that leads to a greater wind stress going counter to the ocean eddy, and it's going to slow down the current slightly. On the south side, the wind is blowing in the same direction as the ocean current. So that's a less effective or smaller wind relative to the current, less wind stress, and it will pump less energy into the ocean eddy. And so the net effect is to extract energy from the ocean eddy. So the issue, of course, is that if we only measured winds from satellite, we wouldn't need to worry much about relative winds if we just wanted to know what drove the ocean. But if we want to calibrate, we really do want to know the winds and currents together. And so this is a valuable input that we haven't had before. Now, we do have other scatterometers, and this is showing from the World Meteorological Organization's records, the scatterometers that are expected to be flying in the 2030 to 2032 range when ODYSEA would launch. So that includes the European scatterometers, which are on all of these are on sun-synchronous orbits. Most atmosphere measuring satellites are, which means that they measure it 2 times a day. So the European scatterometers are at a 9:30 a.m., 9:30 p.m. time of day. India has OceanSat, which is at a noon and midnight measurement time. And then there are a bunch of instruments that are at 6 a.m. and 6 p.m., including the SAR-based Harmony, which has, as I said, tiny sampling, but very high resolution, and a couple passive instruments, SIMR, which is due to launch in Europe starting in the next few years, and US plan, WSFM, also at 6 a.m. and 6 p.m. So obviously that means there's a big gap in measurements between midnight and 6 a.m. and between noon and 6 p.m. And we'd like to fill that gap. ODYSEA slots into the best time we can get to do that, avoiding some of the problems with difficult orbits. So we're targeting 4:30 a.m. and 4:30 p.m., really closing out this scatterometer Y and providing measurements that will get us a better sampling through the course of the entire day to look at the evolution of storms and to better sample the diurnal cycle. So if we're measuring winds and currents with a 1,500 kilometer wide swath globally, then the question is, what do we do with that information? So the ODYSEA, there are many things you could envision doing. The ODYSEA proposal was constructed with 2 science objectives and 1 applications objective. And I'm going to go through those fairly succinctly now. I know that there are many other things people could think of doing, but the first thing to think is, if we've never measured winds and currents together, then this is a really important opportunity to look at how winds and currents couple together. We know that wind stress curl at the ocean surface is linked to vertical motions in the atmospheric boundary layer. And then the question is, how is that wind stress curl modified by the presence of ocean currents? So you can, if you look at the lower panel here, you can see a current, which is this yellow line here running through this thing, through the 4 panels, with a prevailing wind blowing across it, which is the purple vector. And when you look at the literature, there are multiple different hypotheses for what to expect in this case. Some studies suggest that there's not much response to the wind interacting with the current, so that there's no real impact on winds and no induced vertical motion. A second category of studies suggests that there's a response in the curl of the wind, which leads to a local impact on the winds, but nothing remote. And a third set of studies show a substantial local and remote response. So to really tease this apart, we're in need of observations, and that's something that ODYSEA will provide. The second set of science objectives are focused on the fact that we've never really measured total surface currents in a global sense. And so this is an opportunity to really look at how currents vary and how they respond to different environmental conditions. If you look at the climate literature, there's a hypothesis that in a changing climate, we'll see shallower mixed layers and higher stratification that will confine the upper ocean currents to a thinner layer and lead to faster surface currents. So on a climate scale, this is what climate models show. Deep mixed layers correspond to weaker currents, shallow mixed layers to stronger currents. Interestingly, when you look at submesoscales, at really small scale processes, we see a completely different response. In winter conditions, when the mixed layer is deep, we see much stronger, a much more energized eddy kinetic energy in the upper ocean. In summer conditions with a shallow mixed layer, there's less energy. And this is attributed to the fact that in winter, the deep mixed layer is able to store more potential energy, which can be converted into kinetic energy with less potential energy. In summer, due to the higher stratification, we see less kinetic energy. So these are two diametrically opposed hypotheses. In the submesoscale case, low stratification means more potential energy storage and ultimately faster currents. So if we want to tease these apart, this really underscores the need for much more extensive global observations of winds and currents. Finally, ODYSEA, by providing winds and currents, will really meet operational needs. The system is designed to provide near real-time measurements of winds and currents that will let us look at storm evolution, that will drive surface wave models, and will support maritime safety and examination of debris transport. So this will support NOAA, the Navy, Coast Guard Search and Rescue, Mercator Océan International, and other agencies across the world. Just to give you a sense of what this means, for surface winds, if we look at wind stress curl, looking at gradients rather than just the straight wind, you can see that in our program of record, which is NASA speak for what we have now and what we're expecting to have, we have a pretty fuzzy view of the wind stress curl, which ODYSEA really pulls into sharp relief with its high resolution winds. And for total surface currents, at the moment, we get a very fuzzy sense of surface currents by putting together measurements from altimetry and other records. ODYSEA will pull that into sharp relief with its new measurements. So a little quick overview of ODYSEA. It's intended to fill a void in science and operational capabilities. There are currently no satellites that measure total surface current, certainly not on a global scale. And there are no US scatterometers that measure winds, nothing with 5-kilometer postings, and no sun-synchronous measurements in the midnight to 6 a.m. time range. ODYSEA's 90% global coverage in less than a day. with a 4:30 a.m., 4:30 p.m. orbit is a real game changer. And it's planned for near real-time data for winds and currents with less than 6-hour latency for currents and less than 3-hour latency for winds. The mission is currently one of 4 Earth system explorers that have been selected for 9 months of further study. That means the science has been reviewed, and we're now under the gun to demonstrate that the goals can be achieved on time and on budget. So we're dealing with implementation questions at the moment. The concept study report, which is a large volume discussion of what the mission can do and how it will do it, it has to be submitted April 17th, and then there will be a NASA site visit sometime in July or August of 2025. And ultimately, in a year's time, maybe November of 2025, NASA expects to select 2 missions with launch dates targeted in 2030 and 2032. So I wanted to talk a little then about what moves beyond this baseline mission and the 2 science objectives and the applications objectives I talked about. In the concept study report, NASA sets up a structure to consider science enhancement opportunities, which is actually an opportunity for NASA to decide to invest more money to further expand the science, and operational enhancement opportunities, which are an opportunity for NOAA to buy in and contribute to facilitating some of the operational capabilities. And also, in general, support for societal applications. NASA has made a big push for Earth science to applications this year, and they're looking for, as the guidance for the concept study report says, high-level data products and software that's usable to the entire science community, and for things that accelerate the use of mission products post-launch to inform decisions. So they're really thinking about getting science into the hands of decision makers. So we've been thinking as a science team hard about how to represent that. So science enhancement and operational enhancement are the things that NASA and NOAA pay for, and that could involve, hypothetically, I've listed some things here, some additional data products. We've talked about trying to do a reprocess of the 5-kilometer winds to make a slightly noisier but higher resolution 1 or 2 kilometer wind data product, especially for coastal applications. There's the possibility of producing a product that would identify ice extent. You could imagine doing something with air-sea gas exchange of CO2 through improved wind statistics or coastal upwelling index, or some efforts to force wave models with winds and currents. So there are things we might imagine building into budgets that we put into the concept study report to help produce products that are directly useful to the community. And then there's a broader question about what the societal applications are, and that includes Navy and Mercator, who are teamed with us, questions about search and rescue and what's needed to maximize search and rescue for the Coast Guard and other agencies across the globe, thinking about weather and hurricane forecasting, atmospheric rivers, and what's done with information about atmospheric rivers. How do you manage reservoirs that store water for summer usage through forecast-informed systems? Better wind data might lead to insights into how to manage renewable energy and offshore wind. And in general, societal applications represent support for what in the past NASA has called early adopters. So we're definitely interested in facilitating discussion about some of that. So how can you get involved? Well, there's some things that are open to everybody. One is that there are opportunities to explore the science ideas that could be done by NASA using the ODYSEA simulator. That's available. It's a GitHub that's a link to from the ODYSEA website. So if you go to odyssey.ucsd.edu, you can find the GitHub and play with the simulator. If you do that, let us know what you find. We'd love to hear about it, know what works and where the opportunities are. We also want to know who's interested in being an early adopter or contributing to operational and science enhancements. So we'd like to have a discussion about that. And we've talked to NASA headquarters about how to represent that. It's clear that if we can figure out how to articulate interests via what's called a letter of commitment, indicating there's a commitment to spend funding or resources if ODYSEA is funded, those have a really strong impact on the selection process. So we're looking to figure out what the applications are and how to show that there's a real commitment to using them. So I'll just finish up with this nice graphic summarizing that ODYSEA will provide the first daily simultaneous global measurements of surface currents and winds at unprecedented resolution. And it is one of 4 Earth System Explorer missions that's been selected into Phase A, with 2 planned to be selected sometime next year for flights, launch dates in 2030 and 2032. And with that, I'm happy to have a discussion and take questions.
Thank you very much, Sarah. Let's give Sarah a big round of virtual applause. And please, if you have questions, raise your hand. Or you can also type them into the chat and I'll read them. David, please go ahead.
Hi, Sarah. Thanks very much for the talk. As you may know, I'm a UK-based researcher. So I'm just wondering, with all of these applications you're talking about, the extent to which anybody outside the United States can participate?
Absolutely. This is, of course, a US and French project, and there is a lot of interest in showing that NASA has a commitment to open data, so the data will all be public immediately to everybody. And there's a strong interest in showing that this is important globally. I think scatterometry is part of a global constellation with multiple countries participating. And if the US makes a commitment to ODYSEA, that's adding to the global constellation, and we're looking for international engagement in this.
Okay, thank you.
Do we have more questions? Meanwhile, Sarah, if you could go back to the very beginning where you were explaining how scatterometers work. There's a question in the chat asking if you could go over that particular bit again of how do you get direction from scatterometers.
Yeah, okay. So what I said is the backscattered energy that comes back to the satellite depends on the orientation of the radar signal, which is coming in the single direction relative to the orientation of the winds. And so if you get multiple looks, you can imagine looking along this curve here at several different places. So getting one look with one amount of backscattered energy and one look with a different amount of backscattered energy, you know the angle. And so from that, you can figure out the wind. And I have some additional figures that help illustrate that in the extras. So let me show that. So the basic idea is that if you have, in this case, this is showing 4 looks. And so you could imagine, so we're looking at wind speed, hypothetical wind speeds on the y-axis and direction of the wind on the x-axis. And you can imagine that if you get, so each of these lines represents an amount of backscattered energy. And so if you measure a certain amount of backscattered energy, you can say, okay, I know that that would correspond to a wind speed of 18 meters a second at 50 degrees and 10 meters a second at 110 degrees. And so what you do by getting several looks, you have several of these hypothetical lines, and then you can look and say, bingo, they all cross at one place. That must be the wind speed and direction. So that's saying 150 degrees at about 11 meters a second. Now, the reality is this is all super noisy, and so it's not always so clear where they intersect. And ODYSEA's trick is to only have 2 looks, but have them be super clean so that we really do know where the intersection point is. So I don't know if that helps. I can say more about that as well.
Do we have any more questions or comments?
Looks like Alexandra.
Yes, I don't know. Can you hear me? Yes.
Yes.
Yes, okay, thanks. So yeah, for the resolution for the winds, you said it's 5 kilometer. I just want to make sure I heard you right. For the currents, you said it's 25, what you were targeting, right?
Yeah, so winds are obviously much stronger, faster than currents. And so there's just a lot of random noise on the currents. And so the notion is that we'll need to do some averaging to beat down the random noise. So
yeah. And the averaging that you plan to do is also temporal, or I mean,
spatial probably, but
yes.
the goal is actually to release the data in its amazingly noisy form.
Oh, yes.
And leave it to the user to decide how to average. So that gives you the possibility of averaging in really elongated boxes along a long, narrow current, or in straight rectangles or squares, depending on the analysis desires.
Okay, but from what you've studied, let's say, you're targeting like half a meter per second, right? At this 25, is that right? Or is it,
at the 5 kilometer boxes, so the individual pixels, the uncertainty is for currents is expected to be half a meter a second. And as an oceanographer, you might look at that and say that's equivalent to measuring nothing, because globally, almost all currents could be described as half a meter a second, plus or minus half a meter a second. But the point is that with average, this is actually random noise, and with averaging, that will beat down the noise, and we will have something that is meaningful and useful. So we've been trying to figure out how to explain this, because we want to maintain the ability to look at small or higher resolution or elongated features, but each of those features, the individual pixels, will be pretty noisy. It's a challenging measurement, and it's good that the airborne instrument is working so well to give us confidence that we will get something.
Okay, thank you.
Mohamed, go ahead.
Yeah, thanks, Sarah. So the previous Alexandre just asked the same question. So the current resolution is 25 kilometers, right? So
an effective resolution of 25 kilometers.
Yeah, you release in a more noisy product.
Yeah.
I think I mentioned to you before that I hope there would be a good path for an application which is like eddy resolving model validation, but with that right, that really depends how good the noise is. So because right, so like the diamond runs that are based on the basis for the ODYSEA simulator, I think the question is how good they are, but what you would normally do is you would have a very high resolution model and run it for a long time, then look at the accumulated biases of these models and violate them, and then validate them with like Argo or whatever, any favorite metric you want to. But if you have a metric that sits on a smaller scale at the surface, you could validate them on a shorter time frame, and then you could, right, because the models will be not very. I think there will be some problems at the SE interface with these high resolution coupled models, and we have currently a very hard time to validate them. And the question if ODYSEA is able to help with that, right? If you can use it as a benchmark on short time scales.
Yeah, and I think as with any satellite, we design conservatively. We hope for something that will get better resolution. So there are question marks going ahead. We don't know exactly how well the performance will work, but we're pretty confident that what's being presented, this 10 centimeter per second accuracy or uncertainty on 25 kilometer scales, is going to be realistic. That is much better than what we're getting out of geostrophic velocities at the moment. So it will represent a big step forward. It doesn't do everything that everybody dreams about. There's the potential for some synergy with something like Harmony, which will have tiny postage stamp samples with higher resolution.
Okay. Yeah. Both will help.
Yeah. There's room for a lot of imaginative work in the coming years.
Tony, I don't know if you wanna, it seems like your comment will be useful for everyone. I don't know if you want to perhaps elaborate on that a bit.
Okay, yeah, I can do that. I was just following up on the previous question, a comment about the expected uncertainty of 50 centimeter current, and that's the requirements for the science topics that we propose in the proposal. But like all satellite mission proposal, we have to have margins, and typically 30% margins is ideal, and therefore the delivered product will have an uncertainty that is better than the requirement of 50 centimeter per second because of the margin.
So if all goes well.
Yeah. And Sarah, would you like to address the question about uncertainty along the coast?
Yeah, that's a great question. The fantastic thing about using Ka band is that we get a really small footprint, and so the uncertainty along the coast will be comparable to the uncertainty everywhere else. So we're expecting really excellent data right up to the coast. We've just never had such a small footprint for a scatterometer.
Sung-Young Kim, please go ahead.
Hey, Sarah, this is Sung-Young. Could you explain a little bit on the how ODYSEA simulator works?
So the ODYSEA simulator is was written to try and replicate both the satellite orbit of so to give you a way to sample a numerical model with effectively a sun-synchronous orbit with a 1,500 kilometer wide swath, and also to add on noise that's characteristic of the satellite noise. And you can imagine that if you're looking at a rotating beam, such as ODYSEA's, you have different amounts of noise depending on where you are relative to the satellite nadir. And so that is also built into the simulator, and you can play with that and look at the effect of different types of noise models. So there's an opportunity to ask questions about the sampling. If I sample on a sun-synchronous orbit with about this swath and I get this many samples, is that sufficient to address my science questions? And there's also an opportunity to say, if I get data with the noise that's anticipated as the upper limit of noise for the satellite or some other measure of noise with variations across swath, what does that do to my measurements? Do I get better analysis if I only look in the sweet spot in the center of the swath? Do I get better results if I use the whole swath? So there's a lot of opportunity to explore what you can do with a satellite that has the capabilities enabled by ODYSEA.
All right, thank you.
David, I'll get to you in just a second. Sarah Nico is asking in the chat if you're only looking for US expression of interest or if you would be interested in Canada, I assume.
We are interested in everybody's interest. And I've been talking to the NASA headquarters. What has been made clear to us is that if we have, we want to do two things. We have space in the concept study report to document applications users. And so we're really interested in just identifying the range of uses that people anticipate and showing what that does for the science community and for applications. But we also have space to, because NASA is interested in applications, I think we also have space to include letters of commitment that show a commitment to pushing through different types of applications or analyses using the data. So if there are groups that are really committed to using it, we'd love to document that. And that's international.
Thank you. Yeah, please go ahead, David.
Hi, yeah, you were saying it can measure currents close to the coast, and there are some very strong currents close to the coast. So I was wondering, is there a possibility of doing no averaging or less averaging of currents in those cases?
Yeah, we are not planning, because we don't want to second guess how people would average, and that's especially true close to the coast. Our baseline data product is intended to be, and this is of course years in the future, but the baseline data product is intended to be a 5-kilometer product that the user can average in whatever way they like. So that will allow people to say, I know that there's a current that runs along the coast, and I'm going to do all the averaging in the along lines of bathymetry or something following a current. Or I'm going to do no averaging because this is a really big tidal current and I know where it is and I just want to see what number I'm getting.
Okay, thank you.
Any more questions or comments? Sarah, I have a quick comment. Towards the end, when you're summarizing your main points, you brought up the need for early adopters. Could you elaborate a bit on that and like how people could actually get involved?
Yeah, I think that's a good point. So it's taken a while for us to unravel this. NASA previously has used a program called Early Adopters. So the SWAT satellite had a big early adopter program, which was really trying to identify applications users who were committed to using SWAT data from the outset to address specific applications. What I am told is that NASA's new Earth Science to Action plan has somewhat replaced early adopters, but the underlying concept is pretty much the same. NASA wants to know how users are going to use the data and who they are. And so we're really interested in identifying who the potential users are and in facilitating getting data and information to people so that they can plan for and become early users of the data to address the broad range of societal needs that might be met by this mission. So that means we're looking for people to express interest, tell us what they're going to do, and I think we have a 5-page allocation to write about this, as well as the possibility of putting in a probably unlimited number of letters of support or commitment at the end of our package. So we're looking for all of that.
All right.
Sorry, may I have a follow-up remark?
Yeah.
Yeah, so along the line of potential participation, Sarah, would you like to discuss ways that institutionals could participate following the SWOT Doppler crossover example? And if so, what would be the timeline for the CalWell campaign?
Oh, that's a really good point. Yeah. I think we saw that the SWOT implemented, for people who aren't familiar with SWOT had an initial 90-day period where it was on a different orbit that was a 1-day repeat. And to really take advantage of that, SWOT proposed a program called Adopt a Crossover, encouraging groups across the planet to run field programs that took advantage of this initial test out period of SWOT to run coordinated field programs, share data. ODYSEA won't go through this change in orbit that necessitates a really quick response, but I think the energy and the learning that came out of that Adopt a Crossover program is something we would love to emulate. And so really offering an opportunity for groups internationally to coordinate field programs that take advantage of the early data from ODYSEA to think about and make measurements that help us demonstrate the success of or the capabilities of the satellite, and also to do that in a coordinated way that lets people work together, collaborate, and share information. It's a valuable way to let people from countries across the planet participate in ways that are a little less expensive than launching an entire satellite, but that are that are really important to the success of the program.
Thank you.
All right. Do we have any more questions? This was really a lovely discussion. I just want to take the opportunity to let everyone know that if you're doing work in this area, we would love to hear about your research. Please, if you would like to present in a future webinar, reach out to myself or to Sarah or any other member of the steering committee. We would love to hear what you're up to and help us support ODYSEA and other future RC missions as well. Sarah, do you have any final remarks?
No, I'm just hoping that we'll hear from people about what they're excited about and what they think are the useful applications from ODYSEA.
Let's thank Sarah again for a wonderful talk, and I'll see you all next week.
Thank
Bye.
you.